So now we will discuss what is first law of thermodynamics for process. The first law of thermodynamics, we know that is your conservation of energy, where energy can neither be created nor destroyed, though it can transform from one form to another form. So statement for your first law of thermodynamics for a process: when a system undergoes a change of state, whenever heat is absorbed by a system, it goes to increase its energy plus do some external work, that is PdV work. So that means, suppose there is a system where you are giving some heat, then what will happen? Some of the heat will be converted to work and some of the energy will be stored inside the system. Heat is energy. If you are giving some energy to a system, then heat energy is converted to work form of energy and some energy will be stored inside the system. So mathematically how we can write? Suppose you are giving Q amount of heat to the system and you get W amount of work from the system, and change in internal energy, that change in energy dE, this amount will be stored inside the system. So why I am writing change in internal energy? Because initially the system has some temperature or some energy, but when you are giving the heat, the property will be changes. If the property of the system will be changes, some of the state will be changes. If the state will be changes, the energy will be changes. So that is your change in energy. So Q is equal to dE plus W. That is only for flow process. That is for flow process where mass in and mass out. In differential form, del Q is equal to dE plus del W. Why you are writing del Q and why you are writing dE? Because heat and work both had the inexact differentiation, path function, and dE, that is energy, at the potential energy, kinetic energy, internal energy, flow energy, these are the point functions. Okay, so I am writing dE. Where Q is the energy entering the system causing an increase in system internal energy by dE. W is the producing some external work PdV. So what is your dE if this is your flow system? What is the dE? Change in flow energy plus change in kinetic energy, change in potential energy, and change in internal energy. That was discussed in your chapter 1 when you were discussing is your energy. Okay. So second statement, when system is stationary, suppose there is a condition when system is stationary and effect of gravity is neglected and there is no flow of mass into or out of the system. System is stationary, that means kinetic energy will be 0. Effect of gravitational is neglected, potential energy will be 0. And if there is no flow of mass into or out of system, that is a closed system or non-flow system. For non-flow system, that flow work will be 0, PV is equal to 0. That flow work will become when it is an open system. So in such case, what is the change in energy? Change in flow energy will be 0, change in kinetic energy will be 0, change in potential energy will be 0. Then what is left? Only change in internal energy. That dE is equal to what? dE is equal to du. So in your equation what I can write? Q is equal to du plus W. Before it is Q is equal to dE plus W, and in this case D is equal to du, so Q is equal to du plus W for which process? For flow process. Sorry, for non-flow process. That is a closed system where there is no mass interaction. What is your du? Change in internal energy. In differential form, it become del Q is equal to du plus del W. This is for which system? This is for non-flow system or closed system. That Q is equal to dE plus del W. That is for which system? That is for flow system, where what is the dE? Change in flow energy, change in kinetic energy, change in potential, change in internal energy. All are the for flow system. Okay. Then del is used for a quantity which is inexact differentiation. D is used as a quantity for exact differentiation. For a change of state from 1 to 2, how can write the statement? Q1 to 2 is equal to du. Integration of du 1 to 2 is equal to u2 minus u1 plus w1 to 2, because w and heat are the work and heat are the path function and internal energy is a point function. So I can write u2 minus u1. Then what is the limitation of first law of thermodynamics? What are the demerits? That it does not explain the direction of process, means no given direction of flow of heat. It never give you the direction where high to low or low to high. It will never give the direction. Only you know that heat will be transferred, but there is not mentioned that heat to high to low or low to high where it will be transferred. That is not mentioned. Second, it does not differentiate between heat and work. All work can be converted to heat, but all the heat cannot be converted to work. This is also a dissimilarity of a heat and work. So these two are the limitation of first law of thermodynamics. Okay. So this problem we will discuss later. Then we go for the, after completion of your first law, we will discuss this one. What is the application of first law of thermodynamics? So tell me, what is the application of thermodynamics? Thermodynamics will be applicable in the automobiles, in your household, when you are cooking food, and anywhere first thermodynamics is applicable. What is the application of first law of thermodynamics? According to first law of thermodynamics, the total energy entering the system must be is equal to total energy leaving the system per unit mass. Per unit mass. What are the assumptions? The following assumptions are made in the system of analysis, that and this application of first law of thermodynamics for your open system. Application of first law of thermodynamics for open system, that is turbine, pump and boiler. So that we will read and we will extract the data from that. So what are the assumptions? The following assumptions are made in the system analysis. That first is the mass flow through the system remain constant. If mass interaction is there, that means it is an open system. That means mass in is equal to, should be is equal to mass out. Fluid is uniform in composition. If you are giving the heat, the fluid composition should not changes. Okay, but that means they should maintain chemical equilibrium. The only interaction between the system and surrounding are heat and work. Only heat form of energy and work form of energy will be interact with the system and surrounding. The state of fluid at any point remain constant with time. That means it is a which state? Steady state condition, steady flow energy equation, or steady state fluid. In the analysis, only potential, kinetic, internal and flow energy are considered. If flow energy are considered, that means it is also a open system. These are the assumptions that you have to remember. Then application of first law of thermodynamics. Suppose see this is a open system, this conduit. The above figure show the steady flow system. This is a steady flow system, that condition of the state does not change with respect to time. That is also assumptions also. And which is a dotted line. The dotted line is your control volume of a system. When you choose a imaginary system in an open system, that is a which had control volume by means of dotted line. At section 1.1, the working fluid enter into the control volume and various form of energy possessed by it. And section 2.2, the working fluid is leaving from the control volume. Okay. See, the inlet section, the fluid will be inlet at a height of what? Fluid will be available at a height of Z1 from the datum line, and fluid will be at the outlet. Fluid will be at a height of Z2 from the datum line. So with a height the fluid is present means it has some potential energy. Clear? So here, as per assumptions, only heat and work should be interact with the system. See here the control volume, heat we are giving, and what you get? We get, see this is a shaft, we get some shaft work. Okay. Then according to assumption, as mass of fluid entering is equal to mass of fluid leaving the system, that means M1 should be is equal to M2 is equal to M. The energy of an element at inlet is given by. So what are the energies? That is your, there is some mass at the inlet M1, internal energy, potential energy because of height Z1, and the fluid has some velocity V1, that is your kinetic energy. So mass I am taking the common, internal energy plus kinetic energy plus potential energy. In addition to this, the fluid move across the boundary and into the system, it does work on the system. When fluid will be moved across the boundary, then it does work on the system, and that work is known as your what? That work is known as your flow work. That is P1 and P1. So what are the energy of element at the inlet? M1 into U1 plus B1 square by 2 plus GZ1 plus P1 B1. Okay. Now steady flow energy equation. What is the steady flow energy equation? Energy in all form entering the system is equal to energy in all form leaving the system. The energy in the all form, that all the form entering the system, it must be is equal to energy in all form leaving the system. Now writing the energy balance for this. So what is the inlet? So at the inlet, energy, all form of energy entering the system is equal to all form of energy out of the system. So see here, heat is the inlet. So what are the energy inlet? Because of Z1 height, that potential energy, internal energy, due to velocity, kinetic energy, and flow work. These are the inlet, and we are mentioning this as a 1. So what are the outlet you get leaving? That you get work, and what you get? Internal energy at the outlet. Due to Z2 height, potential energy at the outlet, some fluid will be flow across this system. So that is flow work will be P2 V2 plus is your kinetic energy because of volume. So what are the energies? Now energy at the inlet will be M1 is equal to potential energy, kinetic energy, internal energy, and flow energy plus heat will be given to the system. So heat addition is positive plus Q is equal to, because of heat addition, what you get? Work. Okay. So what are the energy at the outlet? M2. This should be M2, not M1. This should be M2 into P, potential energy at outlet, kinetic energy at the outlet, internal energy at the outlet, and flow energy at the outlet. So this is the energy we are dealing with the inlet, and this is the energy we are dealing with the outlet. Heat will be given to the system, and that work you get. So you know that what is enthalpy? Enthalpy is equal to U plus PV, internal energy plus product of pressure and volume. So U1 plus P1 V1 is equal to what? Small h1, that is specific enthalpy kilojoule per kg. U2 plus P2 V2, what I can write? That is your H2. And you know that M1 is equal to M2 is equal to M. That is the assumptions. Mass flow at the inlet should be equal to mass flow at the outlet. So the above equation may be written as, what was written? In place of M1 I can write M. Potential energy GZ1, kinetic energy V1 square by 2, U1 plus P1 V1 plus Q is equal to, in place of M2, what I can write? M GZ2 plus V2 square by 2 plus U2 plus P2 V2 plus what you get? Work you get. So work done by the system, is taken as positive because you got soft work. So in place of U1 plus P1 V1, what I can write? H1. So M1 GZ1 plus V1 square by 2 plus H1. U1 plus P1 V1, I can write H1 plus Q is equal to M into GZ2 plus B2 square by 2 plus H into U2 plus P2 V2, that is H2 plus is your W. That is your steady flow energy equation. The steady flow energy equation per unit mass. This is a steady flow energy equation. Per unit mass means you have to divide the mass. If you divide the mass, this mass will be cancelled out. Mm will be cancelled out. GZ1 plus V1 square by 2 plus H1 plus Q by M. What is your Q by M? That is just small q, kilojoule per kg. GZ2, if a mass divided a mass here, so mass will be cancelled out. What is left? GZ2 plus V2 square by 2 plus H2. W by M, that is your small w, that is kilojoule per kg. The steady flow energy equation per unit mass basis, that you have to remember. What is the steady flow energy equation? And accordingly, we have to derive some formula for the turbine, for the pump. Clear? So see, what is steady flow energy equation? M GZ1 plus V1 square by 2 plus H1 plus Q is equal to M GZ2 plus B2 square by 2 plus H2 plus W, that is steady flow energy equation. What is the steady flow energy equation per unit mass? GZ1 plus V1 square by 2 plus H1 plus Q by M, that is small q, equal to GZ2 V1 square by 2 plus H2 plus W by M, that is small w. What is P1 V1 and P2 V2? Flow work at the entering and leaving. Half v1 square v2 square, that is the kinetic energy at entering